rule, and there it is. So the size of the union of sets added to the size of their intersection is just the sum of the sizes of the two sets themselves. And to show this, we'll use more or less everything that we've done so far. So let's enjoy that moment. So how are we going to do that then? Well, first of all, we see a union and we say, I want to talk about adding up sizes here, and I've got a union. Ooh, that's a bit nasty. Let's turn it into a disjoint union. That will make my life easier. So I use the union decomposition principle, and as we've just seen, I can split this union into three disjoint components. I can now use theorem 17, which tells me that I can distribute the size operation across these three and just add them up. Then I do something along the way, which you might think is just me being difficult. Well, I can't pretend that I'm not mischievously difficult sometimes, but that's not what I'm doing on this occasion. What do I mean? Well, here I've quite clearly got them in the order P difference Q, P intersection Q, Q difference P, P intersection Q, and then I just want to add those up. But when I arrive at this line, I've kind of moved them around. So the P intersection Q has sort of come down to here, and then P difference Q has sort of come across here, and this one's come down, and this. What am I trying? Am I trying to confuse you or what? No. I am helpfully rearranging them so that we can use the trick we began with at the beginning of the lecture. Look, the set of elements P, which also satisfy the property, they are a member of Q. And here, on the other hand, is the set of elements in P which do not satisfy the property that they belong to Q. So look, it's one of these partitions. I'm counting elements in P which do and do not satisfy some other property. Aha! So altogether then, I've just got the number of elements in P. And the same here, the elements in Q that do satisfy the property they belong to P as well, and here the elements in Q that do not satisfy the property they belong to P as well. So, as we saw at the start of this lecture proper, that's just the number of elements in Q. So this is another one of the red box rules. Commit that one to memory if you don't already know it. It's a very handy law. Okay. Now then. Finally, I want to tell you about two kinds of sets of sets. And the first of these is very excitingly called the power set. Okay. So, here is both the definition and an example. So, the power set, and be careful of this, we write 2 to the power s, where s is a set, not a number, it is a set. And when we write that, the value of this expression is also a set, is not a number. Be careful of that, very easy slip to make. So what is this set? It is the set whose elements are all the subsets of S, including at the extreme end S itself, and at the opposite extreme end the empty set. So we could write that down as definition. So this says the power set of S is the set of those subsets R such that R is a subset of S. Okay, that's the power set. Now my favourite example for this is Power Pizzas Inc. I don't know whether you must have come between you must have been into umpteen pizza parlours up and down the land, if not around the world. And you know how they do it. They always have this enormous blackboard that's, you know, the Vesuvius pizza or the house pizza and the like Mama makes it pizza and all the rest of it. Okay? And you think, well, come on, this is a bit overblown. I mean, yeah, they seem to have umpteen different kinds of pizzas. But when it really comes down to it, of course, they're just combinations of the different toppings. And that is, they're using the power set of their basic topping set. So here we are, here's the diagram in the back kitchen of Power Pizzas Inc. on a bad day when all they've got left is ham, cheese and tomato. Okay, so here they are. Yeah, and you could give them all a name and you're in business. Right? So here's the kind of full house pizza at the top. Here's the impoverished student pizza with no toppings on it at all. Sorry, that's a joke in bad taste. But anyway, and then you have the intermediate choices where you've got different levels of topping. Okay, so quick one for you. All right, well, yeah, hopefully you're beginning to see this, but let's bring something into view here. That's all very well, but why this strange choice of notation, you might be thinking, and why the name? Right, quick discussion on that with your neighbour.
This is how many sets are in the power set. 2 to the power of the how many items are in the set S is the number of sets in the power set. Presumably.